ever turn this in.
So I'll update the syllabus that's on Schoology, but we've had a bit of a change in plan. So two things are true. We need to make sure that you've turned in your bottle problem because that is on SIS. Quiz 2, if you missed that, we'll be getting that back today. And I think it's just one person, Jacques, you're the only one I think needs to make up that quiz. All right, so last time we talked about more curve sketching. So here we are today having a review day. And then your test next class on the 11th. How about we say or not? How about we do one more day of review, and we'll say 3:15 is your Unit 6 test. So there's a couple reasons. Good. There's a couple reasons why we're doing that. So I can't have you talking while I am. It's just rude. So there's a couple of reasons for that. We want to make sure that this is most likely going to be the last grade of your third quarter. So it's a test grade, so we want to make sure that you go into it feeling confident. And there's just too much hanging out there that people are just saying no thank you to, whether it's the homework. And it's incredibly frustrating to be ready to go every day to a bunch of kids saying no thank you. So we got to dive in a little bit deeper and say, okay, why are you saying no thank you? Is there questions that you need to ask? Is there stuff you still need to do? Is there a lot else going on? Will one day make a difference for you? Our hope is yes. Our hope is that one day's grace will make a big difference. The other difference is I am away all next week. So I would rather have you sitting in the room taking the test with a substitute than starting the next unit. So what we have planned is to take the test on Tuesday, and then Thursday's class will be like a cumulative review day for you to work in groups, doing a little treasure hunt through your notebook. If you don't have your notebook, then through Schoology, and the notes and things that are posted on there. So you either show up with your notebook or your computer. And that activity will most likely be your last grade, classwork grade. Of the third quarter, the test obviously will be a third quarter grade also. And then that way we can start Unit 8 when I see you on the 21st of March. So review today, review on Friday, ask the questions. Even if you're asking me a question all the way back to related rates, asking me a question on optimization, asking me a question on finding the derivatives, just ask the question. Just ask me, how do you do this? I don't get this. How does it all go together? Our stinger time on Friday will be, again, a time for you to complete test corrections and make sure that you are feeling good about that. So here's your day's grace. The question is, what are you going to do with it? So I challenge you to stay on task today. I challenge you to limit side conversations. If you're talking to your friends, I'm going to assume you're talking about problem number 2 or problem number 3. And you ask them a quick question. If somebody asks you a question and you're like, I don't know, I think that's a great question, please ask. Because we all together learn more from the conversations that happen from all of us together. there are 2 different review assignments for each of these days, and they will both be collected, and I'm looking for as much as I can to add into the grade book. So do the work, and it'll end up positively helping you out. Sound okay? So I'll update the assignment sheet on Schoology this afternoon when I get a minute. But just so we're all on the same page. All right, so now I want us all on the same page. If you don't have this homework, go ahead over to the cubby and make sure you get one, because I want everybody doing this together, and I want everybody talking about this together, because graphing each of these ends up really solidifying what it is that we're talking about. For each graph below, sketch the derivative. So what you have here is your f of x graph is your original function, and this is going to be your f prime of x function. And what we need to make sure that you're understanding, we've been diving so deep into this is the original, this is the derivative, this is the second derivative, and we've been talking about when they equal 0, whether they're increasing or decreasing, and critical points and points of inflection. But it's so important that you really have it all in your head, that our conversations really are always about the original graph. So if I want to know minimums and maximums, unless they say specifically of the derivative graph, I want to know of the original graph. My original function is what I'm dealing with in real life. This is the graph of this whatever scenario I have. My strategies when I go to pick it apart include my first and second derivative, but at the end of the day, what I care about is my function. What it is it's doing, where it's going, what's going on. All right, because my function is linear, my derivative is going to be the slope of the tangent line is going to be 1. That's going to be a constant throughout. Make sense? All right. Would you please, with your group mates, share your graphs for 2, 3, 4, and 5. Talk about what you drew, why you drew it, and then we'll talk about and go through it together. Take a couple minutes to talk. When your mark is set, talk.
What is it called?
All right, come back. Let's talk about graph number 2. And what I want you to think about here is I want you to think about basically throwing up whatever content, definitions, ideas you can when your groups are working through each of these. Because number 1 is linear, I know my rate of change, I know my slope is going to be constant. My entire time, this slope is a positive 1. That's why that's positive 1. When I look at an absolute value graph, and it's interesting, we haven't really talked a lot about absolute value graphs. But this absolute value graph has that sharp point. Guess what? That sharp point is where I cannot take a derivative. So the derivative exists every point down to it, just not there. And the derivative exists every point after that, but just not there. So when we talk about continuous versus differentiable, the difference between a continuous graph and a differentiable graph is this sharp point. It's not continuous at an asymptote. It's not continuous at a jump. It's not continuous at a hole. So all those things that make a graph not continuous also make it not differentiable. So those 3 things that we talk about as far as continuity-wise, they also apply to whether or not I can differentiate. But guess what? The sharp point is the only difference. So I have that place where it cannot happen. So here my graph is, my slope is a lovely -1, there it is. Here my graph is a lovely +1, there it is. And in between, nothing, does not exist. What is the derivative at x is equal to 0? Does not exist. That's my next thing I want to talk about. And this is a mistake I make all the time, so you get a smartie every time that you catch me on it. Ready? When we talk about locations on the graphs, we should be talking about our x's. So when we talk about our intervals, it's a conversation conversation in x's. When we talk about where do critical points happen, for clarity's sake, we should be talking about at the x's. So at x is equal to 0, the derivative does not exist. So when you're talking about each of these points, telling yourself it's at whatever x input value is the proper way to go ahead talking about it. If we talk about it as an xy ordered pair 0, 0, the values of those input values on the original graph, the derivative graph, secondary graph, not always the same. The x's are always the same, but those output values are different depending on what graph we're talking about. So we're going to try to be real tight about saying at x is equal to 0, that derivative does not exist. How many people got that? Thumbs up. Got this graph. Good for you. All right, here's number 3. So number 3 is kind of cool because when you think about it, and I can't seem to do my homework without a piece of paper or a ruler or a sticky that talks about, okay, what is this derivative? 0. Here it is. What is happening to my slope of my tangent line? It's getting more and 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 more positive the whole way up to this asymptote. There it is, getting more and more positive. So this is the thinking person might be like, oh, sweet, this must be exactly the same. And if you weren't careful, you went ahead and drew a graph that looked exactly like that and moved on to number 4. Not the case. Because now bring your ruler here. Every single one of your baskets has straight edges and rulers in it. If you're not tracing it with your finger or your pencil or using the straight edge, you're missing out on an opportunity for you to see what is happening to this derivative as I continue along the graph. My derivative starts off, what, positive or negative? What is the slope of my tangent line? Positive or negative? Am I increasing or am I decreasing? I'm decreasing. This is super negative. How negative? Super negative. How steep? Super steep. And that's what drives this down here. So as my x values continue along, I start becoming less negative. Pretty cool. Less negative, less negative, less negative, less negative, less negative, less negative, and I'm getting closer and closer to 0. So here I am getting less, 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 less negative, less negative, less negative, less negative, approaching getting super close to 0. Thumbs up if you got that one right. Not yet. Catherine, you got a question. Go.
Does it not matter that the slope isn't positive on that second part, on the derivative graph? I mean, that the slope is positive and not negative?
So my slope here is getting bigger. Super negative, right? And it's increasing. So
it just matters that it's decreasing?
What's decreasing?
The slope?
My slope is super negative and it's getting less negative. So the value of my slope is actually getting bigger and bigger and bigger.
I don't know how to word this. Okay. I don't know. I'll think about a way to word it and see if it makes any sense.
This derivative value is negative.
Yeah.
Every single thing that I graph here has a negative output because every single derivative here is negative. But my derivative is getting bigger as I go. I start off super duper negative, and I'm getting bigger and bigger and bigger and bigger. If you want to throw a little concavity in there, that's because this is concave up. So my derivative graph is increasing.
Okay, so I think my question is for the original graph that
Yes.
like the part in quadrant 1, the slope is negative.
True.
But for the derivative graph in quadrant 4, the slope is positive.
This is where I'm graphing my negative value. Like, let's say that I have a slope here of -7. Here's -7. Here, and as each slope goes on, my value goes up. This is the slope. This is the value of my slope. If I asked you, what was the slope of this line? -7. Maybe this is -6. And then here, -1. And then here, -0.5.
Okay.
So I'm getting bigger and bigger and bigger and bigger and bigger. So these x values, these input values, at this x value here, what is my slope? It's about -1.
Okay, thank you.
Does that make sense?
Yes.
Okay. And then the conversations of concavity, where we're talking about how my derivative is increasing, that's the concavity of the original graph, not this graph. We don't talk about concavity here. We're talking about the concavity of my original graph. Okay? Are you with me? You ready for 4? Do you think you have it right? Do you need to revisit it? Here's number 4. How did you do? Yeah. So I made some notes while I was doing my homework. I have that habit. I talk to. If you're not with me while I'm doing my work, I'm talking to each problem. I miss you desperately when you're not here. So I'm like, okay, this looks like a cosine graph to me. Your cosine graph starts high. Remember cosine, right? So your cosine graph starts high and then crosses those axes. And if you look at these points here, that makes sense that this is like 3.14, that's pi, right? So I can see that my x-axis values kind of match up. But here's what I graphed that I cared about, and here's how I went ahead and did this. The first thing I did was look at where does my derivative equal 0, and those were my 0 points. Every single time that this this graph flattens out, my derivative is equal to 0 on every single one of these local maxes and mins. Local max, local min, local max. And every single time that happens, that's when my derivative is equal to 0. All right, now it's time to graph the in-betweens. Because if I'm looking at my derivative, right after this 0 is my first derivative value, positive or negative? The first point I graph. What is the slope of my ruler? It's negative, which means this first value that I graph has to go down because my slope of my tangent line is negative. It's negative, 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 getting more and more and more and more and more negative right up until here. That's this point. Because I've stopped getting more negative. I've stopped getting more negative, and now I've kind of turned it around. I'm starting to get, I'm definitely negative still negative, just less negative. I'm not getting more and more negative anymore. I'm getting less negative, less negative, less negative, less negative, less negative. And then what's interesting here is when I hit 0 again, I'm still growing. Right? I've hit 0. The only difference is now my derivative is positive. And I'm getting bigger and bigger and bigger and bigger and bigger. But right about here, I stop getting more positive and I start getting less positive. So that change in concavity happens here and here and here. Each of these times that I changed my direction. And this is what I want you to think about. If this graph continued along the way that it was going, it would go like that. It would keep going up like this, but it doesn't. It's changed. It went this way now. Each point of inflection is where my concavity changes. That's where my derivative graph has a derivative that's equal to 0. That's where the second derivative is equal to 0. This is the graph that proves that the derivative of cosine is the opposite of sine. Do you see it? Here's your sine graph. Here's your sine graph, but it's flipped. Questions on this one? Preguntas, por favor. Okay? Ready for the next one? You want to relook at it? Take a look at your graph. Think about all the conversations that we've had. Are you ready for the reveal? And the crowd goes wild. Yeah. I have a cubic graph, so when I take one level down, my derivative is going to be quadratic. My critical points are where my derivative is equal to 0. Here's where my derivative is equal to 0. My point of inflection is where the derivative of my derivative is equal to 0. So where this flattens out, that's where that's changed. What can I answer? Please ask. You learn when you ask. Give us a way for us to have you look at all three values at the same time. I want you looking at f of x is the output of the original function. F prime of x is the output of my derivative function, meaning the slope of the tangent line. F double prime of x is going to be equal to the rate of change of the rate of change. And we want you just here looking at positive, negative. So let's just look at A for now. Let's just look at A. When I look at A, the output of my original function is 0. My derivative, put your finger on it, is positive. When we start looking at concavity, if your second derivative is negative, now notice I don't have a point of inflection here because I don't see this changing and going this way. So I don't see a point of inflection in this area. So when we talk about where is this graph concave down, it's all the way from here to where it changes. So this negative concavity, as far as I'm concerned, because this arrow tells me I continue in that direction, I'm concave down from negative infinity all the way up to B. So my second derivative is going to have a negative value. They asked me to place the values in increasing order. So if this is negative and this is 0 and this is positive, then those values for that graph are going to be in that order. Are we okay with that? Let's talk about B. My output value for B is positive. My derivative is negative. But because this is a point of inflection where my concavity changes from decreasing to increasing, I change from getting smaller and smaller and smaller to now it's getting bigger. Because that's a point of inflection, my second derivative value is going to be 0. And then that's the order from least to greatest. You with me? C. My output value of my function is negative. My derivative is going to be 0. Slope of the tangent line is going to be 0. Because my derivative is increasing, the rate of change of my derivative is positive. It's getting bigger and bigger and bigger and bigger and bigger and bigger and bigger from B all the way up through forever. Because the slope of the tangent line is increasing, that makes it concave up. That means my second derivative is positive. Turn and talk with your group mates about, did you understand that problem? If you didn't, what do you know now that you didn't know before? Talk. Take a look at number 4. Let f be a function that's continuous. The function f and its derivatives have the properties indicated in the table below. So it's interesting, f is continuous, so it goes on and on and on and on. But how do I have a continuous function and not able to take the derivative? It's continuous, but it tells me I can't take the derivative. Go ahead, Stephen. Yeah, it's going to be a sharp point. We just saw the absolute value graph, so now I'm suspicious it's going to be an absolute value graph, right? So we need to think about, for the areas less than 3, my output values are positive, my derivative values are positive. So my derivative is increasing, my output values are positive. After I hit 3, my output values are positive again, but now my derivative is negative. Okay? And then we have positive values this whole time. So let's talk about this graph. Does a function have any maximums or minimums? I'm going to say there's a maximum at x is equal to 3 because f of x changes. My f prime of x, my derivative changes from increasing to decreasing. Does the function have any inflection points? I said no, because f of x never changes, never passes through 0. So there's never any inflection points because my second derivative is always positive. So I really struggled with this because, and I don't even think that this is right, because all of my f of x values have to be positive, right? Don't I have everything positive? So I graphed the one thing that I knew, but I think I'm going to have to go with an asymptote, right? Because everything's always positive. If this is always positive, it's always concave up. Maybe I like that better. I think I took it down too far because these output values have to be positive the whole time. I like that better. And I played with my different conversations. It can't be a parabola because here I can differentiate. It can't be this. So we had to go here where this goes ahead and sits on the x-axis. Okay? So it's interesting when we talk about how we're doing in class. A lot of times there are kids that like this conceptual stuff and kids that don't. There are kids that like the process, follow the rule, and do the math stuff, and the kids that don't. Talk with your group mates about which you prefer. Go. We're going to do quiz A and quiz B side by side so you can know what it is that we're talking about. So listen up for both. So when we do the first derivative test to analyze the function, we take the derivative, we set it equal to 0, and those are the x points of our critical points. Our critical points are used to determine mins and maxes on the original graph. So if I look at, get the wine bottle off of the school. Okay. If we talk about this cubic function, we'll just say it looks like this. That's basically a cubic function. If we're talking about critical points, that's going to be where my derivative, my first derivative test means find these x values where my first derivative is equal to 0 because something special is happening at those critical points. So the critical point is here at x is equal to 0 and x is equal to 1. When you use your chart to help you determine your mins and maxes, what you're doing is you're looking at the sign of your derivative. If your derivative is positive leading up to it and negative coming out of it, that means that that is a max. If your derivative is negative leading into it and positive coming out of it, that means that that is a min. And it's the value of the input output at that place in the original function. So if you went ahead and entered your derivative into your calculator and used that input output value for your table, you won't get it right because this max happens at 0, 0 and 0, negative 1/2. You avoid this trap of saying the wrong input output if you just say there's a max at x is equal to 0 and a min at x is equal to 1. Do you understand that distinction? These are the input-output points of the original function, but you run the risk of using the inputs and outputs from the derivative function, and you don't want to do that. Okay. State the intervals where it's increasing or decreasing. So then those conversations have to not be inclusive intervals. So no brackets, parentheses, because at any one point we're not changing. So we're looking at our increase leading up to and coming out of. So this conversation is algebra 2. This is algebra 2 memory. All right, that's A. Let's look at B's graph. Here's B's graph or equation. Same thing, it's a cubic. Your critical points were when it is equal to 0 at 4 and negative 2. Same kind of conversation. My slope, my sign of my derivative. You know that your derivative, that 0 is neither positive nor negative. So you can't say this is positive. 0 is 0. So leading up to, my sign is positive. Coming out of it, it's negative. After it, it's positive. So this is the safer way of expressing your answer. There's a max at negative 2 and a min at 4, and those increasing, decreasing intervals. Share with your group, please, what you now know that you didn't know or what you wish you had done differently on the quiz, and your mark it, set, talk. Come back. All right. So we threw out B and C. We threw out B and C, so you should have a line through them. I didn't even read them or grade them. We threw them out. I'm going to tell you why in a minute. Because so many people did not get, and we call this in mathematics like a follow-through error, because if you're not reading the graph correctly, you've got no shot of getting any of these right. So if you screw up on reading the graph in A, your answers for B and C don't even. So it ended up like we had this as a 6-point question. And we ended up saying, okay, we're not even gonna read this because very few people read this graph correctly. So we made this just a 3-pointer. This graph is of the derivative. I'm looking at the graph of the derivative. Here my derivative is positive and my graph is increasing. Here my derivative is negative, my graph is decreasing. Here my derivative is equal to 0, and that is where I have my critical points, my local mins and maxes. So my critical points are going to be where my derivative is equal to 0. You'll notice that anytime I'm doing this, you know how I say I talk to the problems? I'm like, oh, hello, you're a derivative. I've screwed up on you before. I've read the wrong graph before. I've lost points on this before. So I'm going to circle that. This is the derivative. Anytime the derivative is equal to 0. Let's go ahead through and talk about what should have been your answers, and you can grade yourself and see how you did. They're all critical points because my derivative is equal to 0. When we talk about do you have a max or a min, this is going to be a max because here my derivative is positive and here my derivative is negative. My derivative goes from increasing to decreasing. So when it goes from a positive value to a negative value, I have a max. So there's a max at. Here I have a minimum because my derivative goes from being negative to positive. That's what's going to be there. This is not a min or a max. So it's still a critical point. It's still a critical point because I do have an output of 0, but my derivative doesn't change. So that's one of those points where I had something that looks like this, and my derivative went flat and then came back, but I never changed. That's not a local min or max. And then when we can talk about where the function is increasing or decreasing. That was quiz A. Here's quiz B, and this is why we ended up throwing the question out, because when we were looking for graphs to put in, we told ourselves it was a derivative graph. We went to get a derivative graph, but if you're talking about if this is the graph of the derivative, it doesn't hit 0. And I knew I had an uh-oh moment because Jaden, go put a Smarty up. Jaden comes up to me and he goes, should we say the graph ends here? And I told him yes. And then I was like, oh, snap, we screwed up on the graph on the quiz. We have A versions of stuff. We make B versions to kind of dissuade from cheating, right? But a lot of times going and finding another relevant graph is really hard. We thought we nailed it when we looked at these two graphs because we were like, okay, they both continue on. They both have a bunch of hiccups. We should have figured out a way to move this one down here. Then we could have had a good, clean fun. We should have made this a 0. Then we could have had some good, clean fun. But the way that we put the graph on the quiz, we couldn't do it. So then Brady asks the same question. And while I'm figuring out Jaden's answer and I'm texting Miss Holdaway, oh boy, because she teaches her class the day before mine. So her class gets all the mess ups and we quick fix it. So it goes. So she's like, none of my kids said anything. So she went back and she's like, they didn't realize that it was the graph of the derivative. So what we ended up doing, and while I'm trying to figure this out, Brady comes up and asks me a question. And instead of telling him the same thing I told Jaden, I answered differently in my panic. I'm like, no, it continues on. That's fine. So go put a Smarty up for asking. So then I'm talking to Miss Holdaway after class, and I'm like, okay, your kids didn't catch it at all, and 2 of my kids did, and I told them completely different answers. So what we ended up doing was grading you on how you answered. So Jaden should have said there are no critical points because it doesn't ever hit 0. Brady said there's one critical point because I'm anticipating this hitting 0. and they both got it right. So what we were looking at here was the best answer is there's an anticipated critical point here. And guess what? There's going to be one somewhere down here too. So somewhere along way out here, it's going to hit 0. I think, unless it's asymptotic, I don't know. So this point on B, and if somebody wants to argue that's not fair, they get 3 points for less of an answer. The angst that they went through counts as emotional trauma for B. So the best answer here would be there's going to be one local, if it goes from positive to negative, one local max, because the derivative goes from positive to negative, and then intervals, we can talk about that too. But because the derivative is positive this whole way, then that means that your graph is always increasing, just at some wackadoo views. All right, the back was pretty much self-explanatory in matching. Most everybody did well on that. I was kind of shocked at the difficulty that we had with these two graphs when it came to looking at concavity. And what you needed to know, first of all, we'll talk about A first. It's the graph of the function concave down like a frown, concave up like a cup. And because this continues off the graph, we're talking about this positive concavity happening from this point of inflection on forever and ever, because I don't see it changing or bending. Because there's no bend, I'm going to assume it's positive forever. Because there's no bend here, I'm going to assume that this is negative forever. And that point of inflection, again, whether you say it's at x has a value of 1.5 or the ordered pair, that's fine. For those of you interested, here's B's answers. It was just a cubic graph that's negative. What questions do you have? Okay. All right. So let's talk about what you picked up in your warm-up. This is a deceptive worksheet. You're like, oh, sweet. I'm just going to go through. Oh, shoot. There's one typo that we need to make sure that you have. So while you are working on this, would you please change this word, maximum, to minimum? So in J, change that to a minimum. And this one, it asks you for the absolute. So when you're finding that absolute maximum, be careful of that. So here's how this worksheet goes. There are 10 answers, 0 through 9. Cross off each number for the answers. If you complete all the problems correctly, you will cross off each answer once. So what I'd like you and your group mates to do right now is go ahead and look at each of these problems and work together on your mark, set, go.